Okay, we're still in Chapter 5, learning about polynomial and rational functions. And Section 5.4 is polynomial and rational inequalities. So just two objectives: solve polynomial inequalities and solve rational inequalities. So these are a little more complex than what we've been doing. So we need to get a strategy in place. And remember what a polynomial is a function of the form some constant times x to the what power plus a different constant times x to the next smaller power plus and so on down to a1x plus a0, although a polynomial can be as small as just a0. And then linear is a1x plus a0, and quadratic add another term, and so on. So the domain of a polynomial function is all real numbers, or an interval notation from negative infinity to infinity. The degree of a polynomial is highest power on x. And then I just want you to think about, is a power function a polynomial? Then I'll ask you that in class and we'll have a little conversation about that. So here's a couple of examples of polynomials. This is a polynomial. And this one, remember, is not a polynomial, because you can't have fractions in the exponents and be a polynomial and behave like a polynomial. You can be a perfectly good function, but you're not a polynomial. So here's the instruction set for the examples that follow. It says use the graph of the function to solve the inequality. And these inequalities will have three parts to their solutions: a graph, set notation, and interval notation. So when we're asking about where is f of x less than 0, remember that we're asking where is y less than 0. So we're asking about when is the graph falling below the x-axis, because this is the part of the plane, the xy plane, where the y values are negative or smaller than 0. So we can see that this part of the graph is hanging down below the x-axis and this part of the graph. But what we're asking when we're saying solve the inequality is where are the x values that this happens. So it happens from -1 up to 1, not including the endpoints, because it is 0 there, not strictly less than 0. And then it looks like from 2 on up, you get negative y values. So this is the interval notation. Set notation is the set of all x such that x is between -1 and 1, or x is bigger than 2. So that's set notation. Then the graph of the solution set is just the x number line of the x values where the y values on this graph are negative. Okay, so make sure that's clear to you. So the B part says, where are the y values bigger than 0 or equal to 0? So it must be everywhere else. So let's use a different color, and it will be this part of the graph and this part of the graph. So x from -infinity up to x is 1, and then including 1, because we have equals 0 here. And then from 1 to 2, including 1 and including 2. So this is our interval notation. So that's a set of all x's such that x is smaller than 1, or 1 is less than or equal to x, which is less than or equal to 2. And then the graph of the solution set is all the x values smaller than, this should be -1, sorry. So make sure the entire number line is represented somewhere. So we have from -infinity up to -1, then we have from -1 to 1, then we have from 1 to 2, and then we have from 2 to infinity. Okay, we got everything covered. So if we're given an algebra equation and not a graph, we're still trying to think of the same things. We're trying to think of x values where the y values are either positive or negative. Well, in order to do that, we want to rewrite the inequality so that there's a polynomial on the left and 0 on the right. So we'll have 3x cubed plus 15x squared is less than 0. So we've got to have that 0 on one side because we only know how to work with polynomials and find important points when we have them equal to 0. So the worst thing you could do is divide both sides by x squared because you don't know if x squared is 0. So you can't divide by it. So the very first step is to get 0 on one side, just like when you're solving polynomial equations. So then you're going to find the real zeros. So that's the same thing as solving the equation 3x cubed plus 15x squared temporarily equals 0 to find the zeros. So we're going to factor out the GCF of 3x squared, leaving x plus 5. So using the zero product property, either 3x squared equals 0 or x plus 5 equals 0. So x equals 0 or x equals -5. So these are our real zeros. So these are the only places where the graph can cross the x-axis. So recall that we have two scenarios. You either bounce and touch the x-axis or you cross the x-axis, and we don't know which it is, but we know that zeros are the only place where you can cross. So we use the zeros that we find to divide the number line into intervals, and hopefully this seems familiar because I started you using this process when we were talking about quadratic polynomials. So we have the interval from -infinity to -5, from -5 to 0, and from 0 to infinity. So here are our intervals. We're going to pick a test point. Let's pick -10. And you can either go back to your original inequality or to this one where you rearranged. It doesn't matter. So let's go back to the original one. If I put 3 times -10 cubed, I want to know, is that less than -15 times -10 squared? Well, -10 cubed, 10 times 10 is 100, times 10 is 1,000. This is -3,000. And I want to know if that's smaller, 10 times 10 is 100, 1,500, than -1,500. And -3,000 is smaller than -1,500. So I get true here. So I want this part of the number line. Okay, then from -5 to 0, let's use -1 for a test point because that's going to be easy to do the arithmetic. So we want to know, is 3 times -1 cubed less than -15 times -1 squared? So we'll get -3 on this side and -15 on this side. Well, this isn't true. So we don't want this piece of the number line. And then let's use 1 in the next interval. And so I'm asking, is 3 times 1 cubed less than -15 times 1 squared? And 3 is not less than -15. So I don't want this piece either. So the only piece I want is, it's a strict inequality, so I don't want to include the -5. So it's from -infinity up to -5. So it's a set of all x such that x is smaller than -5. and we already have the graph of the solution set from our work. So we have a graph, a number line graph of the solution set of values of x that make this inequality true. And then we have interval notation and set notation. Okay, so I'm going to let you try the next one in class. And then I want to do one rational inequality. The solution has to look the same, number line graph, set notation, and interval notation. So the first one, we're going to use a graph to solve the inequality. It says, when is the value of this function y, when is y bigger than 0? Well, here's the part of the xy plane where y is bigger than 0. So look for the pieces of the graph that are in the shaded area. And we have this piece, and this piece, and this piece. So when x is from negative infinity to x is negative 1, the y values are positive. And then from x is positive 1 to 2, the y values are positive. And then from 3 on out to infinity, the y values are positive. So there's our interval notation. Here's our graph of the solution set. And then we have the set notation, the set of all x such that x is less than negative 1, or x is between 1 and 2, or x is bigger than 3. Okay, then the B part says, where are the y values less than or equal to 0? So that's going to be this lower part of the graph. So we want to see where do we find y values that are negative? And we're finding them here and here. So from x is negative 1 to 1. Oh, but we need to include the endpoints now, because equal to 0 is part of our solution set. Union with, we can't include 2 because that's not in the domain of the function. Whoops, 1, sorry. And then up to 2, but includes. Let me try again. My eyes aren't seeing this right. So I like the negative 1 to 0. So it's from negative 1 to 0. This part right here. Oh, and all the way up to 1. I like that better, how he started. Negative 1 to 1. All of that is positive. Negative y values. Okay, and then from x equals 2 to x equals 3. So we can't include 2 because that's not in the domain of the function, and we want to include 3. So let's make sure we have everything from negative infinity up to negative 1, from negative 1 to 1, then from 1 to 2, then from 2 to 3, and from 3 to infinity. So it's negative 1 to 1, including the endpoints, and 2 to 3, including the 3, but not including the 2. So that would be the set of all x such that negative 1 is less than or equal to x is less than or equal to 1, or x is between 2 and 3 with the, or equals 2 with 3. And then here is the graph of the solution set. Okay, and then to do it algebraically, I'm going to make another movie for that because it's going to be a more complex procedure.